Very good morning. Good morning, students. Can you hear me? ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? Yes, yes. Very good. Okay, I am sharing the whiteboard now. Can you see the whiteboard? ಕಾಣುತ್ತಾ whiteboard ನೋಡಿ? Yes, yes. Okay. Yeah, keep ready your APL. So we stopped till the progressive wave properties, characteristics of progressive wave. That means for related to mechanical wave we studied. Now the next concept is speed of transverse wave in a string. Speed of transverse wave in a string. That is the next concept. Yes. Speed of transverse wave. So we know transverse. What is the meaning of transverse? Transverse means it is the wave propagate perpendicular to its direction of propagation. Correct, no? So transverse wave in a string. Let us consider a string, okay, of length L and which is attached to a rigid support. So just I'm taking a rigid support here. This is a rigid support and I'm taking a string now of certain length L which is attached to a rigid body. So when you plug the string, okay, when you disturb this string, so you can see this wave shaped on a string, correct now? So this is what the transverse wave, it goes like a crust and trough on a string, right? These are the crust and these are the troughs, correct now? So it goes like a crust and trough. So this is a transverse wave. So now this is a rigid support. See here, you will disturb the string from one end. From this corner, you will disturb. So the wave travel with certain velocity v here till it reaches to the boundary. Okay, this is the boundary here, rigid support. And once it reaches to the boundary, again it get reflected back. It will get reflect back from the boundary again. Okay, now we are going to find out the speed of this wave in a stretched string, okay, or in a disturbed string. So with what speed it goes, that we are going to find out. Now consider a uniform string of length L. Its length is L, let it be. And between the point A and B, it is stretched. Let it be between the point A and B. You can also fix another end. Okay. Let M be the mass of the string. Be taken as a capital M. This is the mass of the string. And T be the tension. Tension in string. Okay, therefore mass per unit length, or we also call it as a linear density. So that is M divided by L. Okay, you can see here the linear density mu symbol we are using mu. So it is mass per unit length. We call it as a linear density. Okay, so if the wire is plugged, a transverse wave is set up, as you can see in the diagram, and it travels with a speed of v is equal to root of t by mu. So remember to find out the velocity of a wave, transverse wave on a string. So that is root t by mu. So you can call it as equation 1 now. Hence, so we can tell that the speed of the wave along a stretched ideal string depends only on the tension, correct? No, from this formula. So it depends on a T and the linear mass density mu. It depends on a mu also and does not depends on the frequency of the wave. Okay. So here velocity V doesn't depend on the frequency. Okay. Now, in the next part, if you want to see the linear mass density, we have taken mu as a m by L. You can see under note point this one. Under the note, it is the mu is equal to m by L. We know that. And this mass can be converted into density into volume. Density into volume divided by the L. So density, we can use the symbol rho. And the volume of the wire, okay? See, the string means it is a wire, no? It appeared to be cylindrical in shape. So of length L we selected. So area will be pi r square. So it is pi r square into L, whole divided by the L. Got it? So we get mu as a rho into pi r square. So by this formula also, see, just by knowing the radius and its density, we can find out the mass per unit length of the string. So what is the rho here? Density of the string. So it depends on a material. For a steel wire, its density is different. For iron, it is different. Okay, aluminum, it is different. And this is the radius of the string. So now by substituting this value in the equation 1. So here we have now V is equal to root T by mu. So substitute here. Therefore, equation 1 becomes V is equal to under root T divided by rho pi r square. Correct now? So here you can tell that V is inversely proportional to root of r square. That means V is inversely proportional to R. What does it mean? So R is the radius of the wire, correct no? This is the radius of the wire. So if the radius increases, thickness of the wire also increases. As the thickness increases, radius increases, speed in that wire or in that string decreases. So the wave travels with a lesser speed. Okay. So this is the relationship between speed of the transverse wave and to the thickness of the wire. Yes, just copy it now. Write down, start writing speed of transverse wave in a string. You can have one rough diagram like this and you start writing completely. Yes, next one. To find out velocity of sound. Okay, what kind of wave the sound is? The sound is longitudinal wave. Okay, it is a longitudinal wave. What does it mean? The longitudinal means the longitudinal waves are the waves which goes like compression and rarefaction. Okay, so like this compression, rarefaction, compression and rarefaction will be there, alternative. So in the compression region, the pressure difference, the pressure is more, correct no? But in the rarefaction, the pressure is less. I can call this pressure as a P1 here in the compression region. This is the P1 and here rarefaction pressure is P2. So here the P1, here the P2. Here is the P1, P2. So where the pressure is greater here, the pressure is greater in the compression region because more air molecule density, correct now? So P1 is greater than P2. So the velocity of the longitudinal wave in a gaseous medium, it is given by V is equal to root B by rho. What is this B here? The B is called as a bulk modulus. Okay, you will study this in a mechanical properties of solids. Bulk modulus. So it is a modulus related to volume stress by volume strain. Okay, so you can also make a note. So this is the volume stress divided by volume strain. Okay, it is basically related to change in volume. And rho is the density of the gas. Density of gas it is. See here, density of gas, if it is increases, then the speed of sound decreases according to this relationship. V is equal to root B by rho. It is inversely proportional. Okay, and as we know that the speed of sound, what is the speed of sound? So it is approximately 332 to 334 meter per second. Correct, no? This is the practical conclusion. So speed of sound is 332 meter per second, and sound waves are longitudinal waves. Okay, so it goes like compression and rarefactions. So here the first assumption is from Newton. So we call it as a Newton's formula. Newton given one formula to find out the speed of the sound in a gaseous medium. According to Newton, see here the reason for the pressure variation. See here P1 and P2, P1 and P2. So there is a variation in pressure, correct? So this is due to isothermal. Okay, pressure variation in a medium. Can mention here pressure variation in a medium during propagation. Propagation means a movement. Propagation of sound is isothermal process. So this is the Newton's assumption. It is an isothermal process. So we know that what is the meaning of isothermal process, right? Yeah, I will ask anyone you to answer now. Impana unmute. What is isothermal process?
Sir, constant temperature.
Very good. Okay. So it is the process where the variation of pressure and volume occurs at constant temperature. So we can write that PV as a constant. Correct. And if you differentiate it, so we get P into dP plus V into dV. Correct, no? We get this one. That is equal to some 0. So P dP is equal to minus V dV. Therefore, dP by dV is equal to, what we get, minus V by dP by dV is equal to minus V by P. Therefore, the P will be, check here, what will be the P? P dV V dP. Okay. Yeah, 1 minute, 1 minute. This is a P dV and dP. So we are differentiating based on the product rule. P dV V dP, P dV and V dP, and here dV divided by dP will be V by P. Therefore, P will be minus V by dV into dP. Okay, see here, this is what the bulk modulus factor. I told you, volume stress by volume strain. So it is basically the volume changes. Okay, this is the bulk modulus. So this P, pressure, can be taken as a bulk modulus now. Bulk modulus B. Okay, so this is the Newton's assumption. Now substituting this value, call it as a equation 2. Substituting this P is equal to B in the equation 1. Substitute there. Therefore, equation 1 becomes V is equal to root of P by rho. So this is a Newton's formula for finding the speed of the sound. Okay, theoretically we got, but we know that the practical value 332 meter per second, correct? No, we should get now by substituting the pressure and density value. If you substitute here, then you should get that answer. Let's check that. Now at STP, standard temperature and pressure for air. So we know that atmospheric pressure value 101.3 into 10 power 3 Pascal, kilopascal we say, and density of air 1.293 kg per meter cube it is. Now substitute, this is 101.3, 10 power 3, and here 1.293. So after calculating, we get 280 meter per second. Okay. So, but velocity of the sound is coming very less here, according to theoretically by using a Newton's formula, but actual value is 332, correct? No? So hence Newton's formula fails to explain the speed of sound. Okay. So this is about 16% less, correct? No? So actual experiment value of practical value of speed of sound is 332 meter per second. Hence, Newton's law of sound fails to explain reason for speed of sound. Okay, so this is the Newton's. Yeah, you all can see the board clearly. Yes, visibility is good. Okay, very good. The next one. See here, the Newton fails to, predict the exact value of the speed of sound because he assumed that the propagation of sound in a gas medium is an isothermal, but actually it is wrong. Okay, so it is corrected by the one more scientist called Laplace. Okay, we call as a Laplace correction. So what he corrected, according to him, okay, the propagation of sound, so in a gaseous medium, so will obey adiabatic process. It's not an isothermal. Okay, so that is the assumption. Propagation of sound waves in medium means in a gaseous medium is adiabatic. It's not an isothermal, it is an adiabatic. So adiabatic means we know that PV power gamma is equal to constant. So what is the gamma here? Gamma is the specific heat ratios, right? So gamma is Cp by Cv. So now by differentiating this, okay, differentiating, what we can get again like dP by dV, same like the previous equation, but the gamma factor will be multiplied for that, minus P by V. Therefore, minus gamma P is equal to minus V dP by dV. Anyhow, this is a bulk modulus. Okay, bulk modulus. So that can be taken as a B. Therefore, gamma P is equal to B. So now in the equation 1, see here, this is the equation 1, right? This is what we have here. In this equation, in the place of B, we should replace from equation 1. We know that V is equal to root B by rho. Therefore, V becomes root of gamma P divided by rho. Okay, now you can substitute all the values. Okay, for air, no? For air. So what is the gamma value? Gamma value, Cp by Cv value for air, it is 1.41. And P value as it is 101.3 kilopascal into 10 power 3 Pascal it is. And rho value, density of air, 1.293 kg per meter cube. Yeah, substitute this value, substitute and calculate. Now tell me how much you get the answer. Substitute in this equation. So is the Laplace formula. We generally call it as a Newton-Laplace formula because he taken the support of Newton's formula also, right? So we call it as a Newton-Laplace formula. Yeah, substitute and tell me the answer, how much you get. Calculate it. Use the calculator and do the calculation. Java Sharif, Raghavendra, Sai Raghavendra, 332.48. Student, better you put your name, okay, in your ID, or else the ID will be removed from the class. Kinshu Priya, okay, 332.75, 332.38. Yes. So after substitution, we are getting the value of V, velocity of sound, as a 332.38. 332.38 meter per second. This is what our practical value also, correct? No? See, practically the same is the speed of the sound. So this is the Laplace correction. So generally you get the question for a 5 mark to explain the Newton's Laplace formula, okay, or to derive the Newton's Laplace formula for the velocity of the sound. 5 mark question. If you get individually, then it is a 3 marker. Let's copy this Laplace corrections. It's next topic. Effect. Factors affecting velocity of sound. What are the factors affects the velocity of sound? That is the next one. Write down, take the heading. Factors affecting speed of sound. So as per the formula, see here we know that V is equal to gamma P divided by rho. So now this formula as a reference, okay? Gamma means what? Cp by Cv, no? Yeah. So here the first factor is effect of pressure. Let's see, will it affect the speed of sound or not? Effect of pressure, the first factor. So here PV is equal to constant, correct? So at constant temperature. So if the process carried under at constant temperature, then PV will be constant. So thus If pressure increases, what happens to the volume? If pressure increases, volume will decrease. See, there is a variation. If pressure changes, volume will change. Correct now? So if volume decreases, what happens to the density? Volume decreases. Volume. See, this is the bigger volume, a smaller volume, and this is a bigger volume, let it be. So here volume decreasing. Decreasing means the smaller one. Then what happened to the density? So density of the air molecule increases. Correct now? Density will increase. If pressure increases, volume decrease. If volume decrease, density will increase by the same factor. Hence, if you select this P and density ratio, P by rho, it comes as a constant only. Okay, it remains as a constant. Therefore, we can say that velocity of sound is independent of the pressure. It is not affected by the pressure of a medium. Okay. So this is the conclusion. Velocity of sound is independent of pressure. Okay. In terms of graph also you can understand this. If we draw the graph, see sound versus the pressure. So this is the speed of sound. This is the pressure. Okay. So the speed of sound remains a constant. It never varied. It just comes like a one horizontal line like this. So pressure doesn't have any effect. So this is the effect of pressure. Copy this one. In gaseous medium, is directly proportional to square root of its absolute temperature. So here approximately 0.61 meter per second per degree raise in temperature. So, okay, so that much of speed will be increased. If you raise 1 degree Celsius temperature, then approximately the speed of sound will be raises by 0.61 meter per second. Let's copy this one. So it is directly proportional. Effect of humidity. What is the meaning of humidity? Means the presence of moistureness in the air. Okay, so depends. See here, generally we know that the moisture air, like moist air. What is the meaning of moist air? It is the air mixed with water vapor. Okay, so moist air has less density. Remember this, moist air has a less density compared to dry air. Compared to dry air. Very, very important. Okay, so density of moist air is lesser than a dry air. Therefore, what happens here? See, in the formula, we know that V is inversely proportional to rho. Square root of rho, correct? No? Since the formula is what? V is equal to gamma P by rho. So here V is inversely proportional to rho. As a rho means density. Density decreases its velocity increases. Okay, the velocity of sound will increases. Therefore, speed of sound is greater in moist air than dry air. Very, very important. Underline it. Because moist air has a lesser density. Let's copy this point. Effect of humidity. So what you can say? So velocity of sound in a gaseous medium increases with increase in humidity. So that is a conclusion you can write. Okay. Therefore, velocity of sound or speed of sound in a gaseous medium increases with increase in its humidity. Its humidity means medium humidity. Medium humidity. Let's copy this. So effect of frequency, speed of sound in air is independence of its frequency. So whatever the sound travels, might be frequencies are different, but it travels with the same speed. I'll explain you once again the relationship between speed of sound in gas and the RMS speed of a molecule. Okay, so this is the velocity of sound, gamma p by rho, that can be written as in terms of temperature 3 gamma RT by m. And for the RMS speed, Vrms, root 3 RT by m, that is 3p by rho. We can write it RT by m as a p by rho. Now divide these two, equation 2 divided by 1. We get Vrms by V sound as a gamma root 3 by gamma. Therefore, this is the relationship. V sound is equal to gamma by 3 whole power of. But this value is always comes lesser than 1. So that shows that the velocity of sound always lesser than the RMS speed. Very, very important for the competitive. Yeah, let's revise what we discussed today. So we discussed from the transverse wave in a string, correct? From here, I think all of you understood about today's lesson. This is the speed finding formula. V is equal to T by mu. Mu is the mass per unit length or linear density of the string. And we can also have one more formula in terms of its radius and temperature or tension. P by rho pi r square. And velocity of sound, it is V is equal to root B by rho. B is the bulk modulus. And Newton's formula, the reason for the failure of Newton's formula is he believed that it is an isothermal process. So we got this formula P by rho, and according to this Newton's formula, we are getting 280 meter per second. So here it went wrong. Okay. Hence the Laplace correction has came. So according to Laplace, the process is what? It is an adiabatic process. It is. Adiabatic means PV power gamma equal to constant. There is no exchange of heat and all, right? So PV power gamma equal to constant, and we are getting the Newton's Laplace formula here. So by using that, we get the V value 332.38 meter per second. So which is equal to the experimental value. Hence, it is believed that this formula is correct. V is equal to gamma P by rho, and the process, what is happening when the sound is propagating in the medium, that is adiabatic. Okay, it's not an isothermal. And the next factors affecting the speed of sound, here pressure is independent on the speed of sound. So it is not affected by the pressure. Whatever the different pressure, the speed of sound remains constant. You can see the graph here. And effect of temperature. So V proportional to root T. So it is directly proportional to temperature. Okay. And effect of humidity. So directly proportional again. As the humidity increases, speed of sound also increases. Okay. And next, there is no effect of frequency of sound. It is independent. And finally, we studied the relationship between speed of sound and the RMS speed. Okay, so speed of sound is always lesser than the RMS speed because this gamma by 3 value comes lesser than 1 only. Whatever the value is, substitute here gamma. Okay, like you can choose 7 by 5 or 3 by 2, 5 by 2. So the value comes as a lesser than 1 only. Hence, its value will be lesser always. Okay. Yes, I hope you understood in today's lesson. And today's homework for you is take down, write the question for homework. Derive an expression for Newton's Laplace formula for a speed of sound. Derive an expression for Newton's Laplace formula for the speed of sound. And take the one more question. Just I will write it on the board now. This is a homework for you. Homework question. Compute the ratio of speed of sound in hydrogen. Speed of sound in hydrogen to the RMS speed of hydrogen molecules. Hydrogen molecules. So it is basically depends on the speed of sound to the RMS speed. This is the hydrogen gas. You can call it as a hydrogen gas. Yeah, this is your homework. We should find out the ratio between these two. Hydrogen gas to hydrogen molecules. Okay. Yeah, do it and show me tomorrow. Yeah, bye all of you.